For his remarkable contributions to material science, Michio Kaku has asserted that the James Webb Space Telescope JWST has discovered 6 enormous structures that experts previously deemed impossible. This observation holds enormous potential to revolutionize our understanding of the universe. It challenges current theories about galaxy formation, evolution, and the timing of complex structures in cosmic history. The findings are both thrilling and transformative, bringing into question well-established ideas about the nature and origin of galaxies. The fact that such assertions are coming from a renowned expert like Kaku adds weight to the significance of these discoveries and emphasizes the necessity of keeping an eye on forthcoming developments. Michio Kaku is a prominent and respected figure in the scientific world. He is a physicist of American and Japanese heritage with expertise spanning traditional experimental physics and quantum mechanics. Unlike many conservative scientists who are slow to embrace new ideas, Kaku has consistently been open to the groundbreaking discoveries coming from the JWST mission. His enthusiasm for sharing these new insights with the public demonstrates his commitment to broadening our cosmic knowledge. It is notable that Kaku has chosen to speak openly about these findings, which he believes can no longer be dismissed or ignored. His energy and focused perspective come through in his discussions of these recent discoveries, showing a scientist who is deeply engaged in the implications of what he calls revolutionary revelations from the James Webb Space Telescope. These revelations invite us to dive into the implications of Kaku's latest disclosure regarding these 6 colossal structures. Kaku has always been an innovator, unafraid to explore new ideas throughout his career. He has long been willing to consider theories that challenge the established order, fully recognizing that even groundbreaking models like Einstein's relativity and Newton's laws, while foundational, do not completely capture the universe's complexities. He understands that these latest discoveries by the JWST offer opportunities to push the boundaries of cosmology, even though many of his colleagues are not yet convinced. This reluctance among some scientists has led to concern, sleepless nights, and debate within the community, especially among proponents of the Big Bang model and critics of quantum mechanics. However, Kaku meets these reactions with amusement, seeing the resistance as further proof of science's enduring capacity for surprise and evolution. The JWST's recent discoveries include 6 colossal galaxies dating back to the universe's earliest periods. Each of these galaxies, remarkably, has more stars than our own Milky Way, despite having formed only 200 to 700 million years after the Big Bang. This is a period previously considered too early for such massive structures to have existed. The research team that discovered these galaxies aptly named them universe breakers, as they have the potential to reshape our understanding of how the cosmos developed in its infancy. These unexpected formations suggest that the universe's early years were far more dynamic and complex than scientists had once believed, challenging the idea that galaxies took billions of years to form and reach their massive, structured states. This forces scientists to consider whether the universe itself might be older than previously thought, or if cosmic structures evolved at a much faster rate than current models can explain. The presence of these structures in the early universe is causing a ripple of discomfort among many scientists, particularly those with a more conservative view of cosmology. Established theories have held that complex structures such as galaxies could not have formed so quickly after the Big Bang due to the time required for stars to cluster and form dense, organized structures. Now, some physicists are raising concerns about the validity of these new findings, questioning whether there might be errors in the age estimates of these galaxies. Kaku, however, is unperturbed by this resistance. He reminds us of the critical role experimentalists play in science, as they are the ones who maintain a healthy skepticism and challenge prevailing ideas when the evidence demands it. According to Kaku, the need for continuous experimentation is a cornerstone of physics and a reminder that science remains an ever-evolving pursuit of understanding. The current model of the universe's origins, which was established in 1927, is based on observations of the universe's expansion, a finding initially revealed by Edwin Hubble. This model led to the conclusion that the universe began from a singular, immensely dense point and has been expanding ever since. At that time, it was difficult for people, including scientists, to imagine a universe with both a beginning and an end. Many found comfort in the idea of an infinite, eternal cosmos. However, new discoveries have continued to challenge this model. Now, the scientific community faces yet another paradigm shift, as the unexpected galaxies identified by the JWST seem to defy current understandings of the Big Bang theory. One of the key tools used to measure cosmic distances and the age of astronomical bodies is redshift. Redshift, also known as the Doppler effect, refers to the shift in the color of light as a light source moves in relation to an observer. When a celestial object moves toward an observer, its light shifts toward the blue end of the spectrum, while it shifts toward the red end as it moves away. This principle, similar to the way sound changes as a car approaches and then moves away, helps physicists gauge the rate at which objects are moving and the distances involved. However, Kaku and others note that even slight errors in redshift measurements can drastically affect our interpretation of cosmic data, especially in a context as vast and intricate as the universe. As such, the measurement methods currently in use are under review, as scientists evaluate whether these massive structures truly reflect accurate redshift readings or if some underlying calculation errors exist. This investigation underscores the need for flexibility in the scientific process, as well as the importance of rigorous re-evaluation. In light of the JWST's findings, it is increasingly clear that scientific theories must remain open to re-examination. Kaku notes that while theories provide a framework for understanding, they are not immutable truths. Instead, science demands that these frameworks evolve as new data emerges. Early 20th century discoveries, such as Hubble's demonstration of the expanding universe, altered humanity's understanding in unprecedented ways. The observation that galaxies are moving away from each other, a phenomenon known as Hubble's law, suggested that the universe is dynamic, constantly growing and evolving. Today, with discoveries like those from the JWST, scientists must again confront the possibility that even well-established theories may need revisiting. The JWST's detection of galaxies from the universe's earliest epochs is another example of science's capacity to challenge and redefine. The telescope's unprecedented sensitivity and resolution allowed scientists to view galaxies far more advanced than expected for their age. Among these finds are 6 massive galaxies, each possessing an unexpected level of size and luminosity, known as the universe breakers. These galaxies' existence suggests that the universe's foundational structures were more developed and elaborate in the first few 100 million years than prior theories accounted for. Their detection adds fresh insight into one of cosmology's most persistent mysteries, the nature and progression of galaxy formation. Galaxies, often described as cities of stars, consist of gas, dust, and dark matter, all bound by gravity into complex, vibrant systems. Their formation and evolution are critical, not only to understanding the universe but also to testing key theories such as the Big Bang. Nearly a century ago, the Big Bang theory emerged, proposing that the universe originated from a single, infinitely dense point and has been expanding since. This view was largely supported by evidence like the cosmic microwave background radiation, which is seen as the afterglow of the universe's formation, and the redshift of distant galaxies, which corroborated the concept of an expanding cosmos. However, the latest discoveries from the JWST challenged these foundations, suggesting that galaxies developed more rapidly and on a grander scale than previously thought possible. The recent findings from the JWST implied that the universe's structure and evolution may be far more nuanced and complex than traditional models can fully explain. These revelations continue to push the boundaries of scientific understanding, encouraging scientists worldwide to question, investigate, and embrace new paradigms. As each discovery adds depth to our comprehension of the cosmos, it also underscores the importance of open-mindedness and continuous inquiry in science. Through every unexpected finding, like those from the James Webb Space Telescope, our understanding of the universe expands, reshaping human knowledge and redefining our place within the vast and mysterious cosmos.